Hello and welcome to Unacademy, a one-stop destination for all English medium civil service aspirants. Welcome to Science and Technology Simplified. In this session, we'll discuss superconductors and their applications. Before we start the session, a very important announcement. If you are preparing for 2026 and beyond, you can get all our GS and CSAT courses for just 17,999 plus free access to our exclusive UPSC mains course, the Nishchay 2026. This is a limited period offer, so do enroll before it is late. Don't forget to use the code IAS English and participate in our mega lottery as a part of Dil Se Diwali, the Unacademy Utsav 2025. Let us now continue with the session on superconductors. What is a superconductor? Superconductor is any material that can conduct electricity with zero electrical resistance. And the material will get this property when it is cooled below a specific temperature. Below this temperature only the material behaves like a superconductor. Below this temperature only it will conduct the electricity with zero electrical resistance. And such temperature is called as critical temperature. Let us understand about the critical temperature with these examples. Here are some examples of superconducting material. One example is mercury. Mercury's critical temperature is 4.2 Kelvin. It means above 4.2 Kelvin, mercury is a normal material. But below 4.2 Kelvin, mercury becomes a superconductor. Let us see one more example. Niobium titanium alloys. These alloys above 10 Kelvin, they are normal material, not superconductors. But when these alloys are cooled below the 10 Kelvin, then they will behave like superconductors. It means they can conduct electricity with zero electrical resistance. In the same way, I have given the examples of more superconducting material along with their critical temperatures. And also I have given some special features of those superconducting material. For example, mercury's speciality is it is the first discovered superconductor. And niobium titanium alloys speciality is it is used in the MRI machines. Magnetic resonance imaging, we will use it for medical imaging purposes like cancers, brain tumors, etc. We also use niobium titanium alloys in the particle accelerator. What is the best example for the particle accelerator that we know? That is the Large Hadron Collider. This Large Hadron Collider was constructed for discovering the Higgs boson particles. Higgs boson particles. These particles are also called as God particles. We believe that these Higgs bosons are responsible for all other particles to get their mass. And in these particle accelerators also we need superconductors. We need superconductors in MRI machines, particle accelerators, and in these two types of instruments we use a superconductor called as niobium titanium alloy. Another example is niobium tin alloys. Their critical temperature is 18 K. It means above 18 K they are normal material, but below 18 K, if you cool them below 18 Kelvin, then they will behave like superconductors, that is conduct electricity with zero electrical resistance. and they can be used in making powerful electromagnets. Same way, ceramic cuprates, their critical temperature is 90 to 130 Kelvin. Above 130 Kelvin, normal material; below 130 Kelvin, superconductor. Specialities, these are the first high temperature superconductors. Then you may get a doubt about what are these high temperature superconductors, low temperature superconductors. Do we have different types of superconductors? Yes, we have different types of superconductors. In the later part of this class, we will also discuss the types of superconductors. For the time being, ceramic cuprates are high temperature superconductors and their critical temperature is 90 to 130 Kelvin, and these are the first high temperature superconductors discovered, that is their speciality. Next, yttrium, barium, copper oxide, their critical temperature is 92 Kelvin and they allow high temperature superconductivity. That is another example for high temperature superconductors. Okay, same way, bismuth, strontium, calcium, copper oxide, critical temperature 107 Kelvin, and these are also high temperature superconductors and we use them in making the wires. And mercury, thallium, barium, calcium, copper oxide, and its critical temperature is 133 Kelvin. That is above 133 Kelvin it is a normal material, below 133 Kelvin it is a superconductor. What is its speciality? It is the highest critical temperature non-cuprate superconductor. Means usually cuprates are high temperature superconductor. It is not a cuprate, but it is one of the highest critical temperature superconductor. In general, which superconductors are more commonly used or which are easy to use? High temperature superconductors are easy to use. For example, if you take mercury, its critical temperature is 4.2 Kelvin, which is a very low temperature, cryogenic temperature. So cooling mercury to 4.2 Kelvin is very difficult. We have to maintain cryogenic temperatures, we have to maintain them for all the time in cryogenic temperatures, which is very costly and also needs a very sophisticated instrumentation to maintain that. So therefore, high temperature superconductors are easy to be used because we can easily cool down the material to 133 Kelvin. And we have given other examples also. Now, most important to mention are non-conventional superconductors, like for example, carbon nanotubes. In general, we know lots of applications of carbon nanotubes, and also we know graphene. We call graphene as a wonder material. We call graphene as a wonder material. What is graphene? This is one atom thick sheet of carbon. This is much stronger than the steel and more conductive than the copper. And if you roll up that graphene into tubes, we call them as carbon nanotubes. And then fullerenes. Fullerenes they are still made up of graphene, but if you roll up graphene into tubes, we call them as carbon nanotubes. But if you roll them up like some balls or spheres or elliptical structures, then we call them as fullerenes. In general, we study about carbon nanotubes, graphenes, fullerenes in the nanotechnology subject. In nanotechnology, they have huge applications. But can we also use them as superconductors? Yes, they can be kept under non-conventional superconductors. For example, carbon nanotubes. Their critical temperature is 240 Kelvin. It means above 240 Kelvin, they are normal material. Below 240 Kelvin, they are superconductors. Okay, but they conduct electricity with zero resistance only along their length but not across. It means if you assume a carbon nanotube, it will conduct electricity like this with zero resistance, but not like this, only along the length but not across the length. Then graphene, its critical temperature is 1.7 Kelvin. Above 1.7 Kelvin it is normal material, below 1.7 Kelvin superconductor. It becomes superconducting only when coupled with calcium. Then we call this calcium as doping agent. And what are the non-conventional superconductors? These are the superconductors which get superconductivity only when added with some doping agents. One example is graphene. Then fullerenes, critical temperature 33 Kelvin. They exhibit superconductivity at relatively high temperature because 33 Kelvin is more than this 1.7 Kelvin. When intercalated with alkali metals, it means they are also non-conventional superconductors because they show the superconductivity only when added with some doping agents. What is the doping agent here? Alkali metals. So this is the complete list of the superconducting material, their critical temperature and their speciality. Now coming back to the original definition. Superconductors are the material that can conduct electricity with zero electrical resistance. But they will conduct the electricity with zero electrical resistance only when they are cooled below the critical temperature. And I explained the critical temperature concept with all these examples. Let us also see the definition of critical temperature. Every superconductor has a specific critical temperature, but it is different for different substances. Like for example, for mercury it is 4.2 Kelvin and for niobium titanium alloy it is 10 Kelvin. Every material will have a critical temperature, but it is different for different material. Below that temperature only it will become the superconducting material. So each superconductor has a specific critical temperature below which it exhibits superconductivity. This temperature is called critical temperature. But with this we understood what is critical temperature, but you may say that all these values are given in Kelvin. It is better we know these values in the Celsius also. So here I have given the formula how to convert the Kelvin temperature, the temperature given in the Kelvin scale into the Celsius scale. Using this formula we can convert the temperature given in the Kelvin to the Celsius scale. And by the way, what is Kelvin scale? We have a particular temperature called absolute zero. Absolute zero. This is the lowest possible temperature. We cannot have a temperature below this. That is minus 273.15 degrees Celsius. To conveniently indicate this, Kelvin scale was invented, and in the Kelvin scale minus 273.15 degrees Celsius means 0 Kelvin. 0 Kelvin is nothing but absolute zero. If 0 Kelvin is equal to minus 273.15 degrees Celsius, 10 Kelvin is equal to minus 263.15 degrees Celsius. Using this formula, you can convert all these values into Celsius for your comfort. That is nothing but the critical temperature. So, material that becomes superconducting, that is conducts electricity with zero electrical resistance below the critical temperature are called as superconducting material, and we have seen a lot of examples for superconducting material. Some of them are low temperature superconductors, some of them are high temperature superconductors, and some of them are non-conventional superconductors. Okay, mercury is a low temperature superconductor. Ceramic cuprates are high temperature superconductors. Graphenes and fullerenes are non-conventional superconductors. Now that we understood about what are the superconductors and what is the critical temperature, now let us try to understand the mechanism by which a material will become superconducting material. It means how it will be possible for it to conduct electricity with zero electrical resistance. Now we are going to discuss some key properties of the superconductors, some important properties of the superconductors. First property that we are discussing is the Meissner effect. Meissner effect. Meissner effect is, here a superconductor will expel all its magnetic field. Let us suppose this is a superconductor. And inside this there will be some internal magnetic field. There is some internal magnetic field, okay, in the form of magnetic flux lines. Magnetic flux lines are there inside this material, okay. And it is a superconductor. It will expel all its magnetic flux lines, all magnetic field. What magnetic field? Internal magnetic field is expelled. It means all the magnetic flux lines will be kind of erased. There won't be any magnetic flux lines in that material anymore. Means it will expel all its internal magnetic field or the magnetic flux lines from its interior when cooled below the critical temperature. When it will expel the magnetic field? Only when cooled below the critical temperature. It means, for example, if you take mercury, mercury expels, this mercury expels means sending out, okay, it will not have internal magnetic field anymore. Expels all its magnetic field when cooled below 4.2 Kelvin. If you cool mercury below 4.2 Kelvin, it will expel, means all its magnetic field will be erased, kind of. It will not have any more internal magnetic field once you cool it below 4.2 Kelvin. This concept of expelling the internal magnetic field when cooled below the critical temperature is called as Meissner effect. Okay. Once it expels all its internal magnetic field, now it do not have any internal magnetic field. When it do not have any internal magnetic field means it is now converted into a diamagnetic material. It is now converted into a diamagnetic material. Okay, listen carefully. When a material will become a diamagnetic material, when it expels all its internal magnetic field. Now you have taken a material, then cooled it below its critical temperature. Then it expelled all its internal magnetic field, means it is not magnetic anymore. When it is not magnetic anymore, we call it as a diamagnetic material. What is a diamagnetic material? A material that can repel the external magnets. A diamagnet is something that can repel the external magnet. This repulsive force we use in magnetic levitation. Observe this particular animation. This is showing a maglev train. This is showing a maglev train, means magnetic levitation train. These trains do not touch, they do not touch the track. They do not touch the track. Because they do not touch the track, there is no resistance or there is no friction. Because there is no friction, very high speeds are possible. One factor that will limit the speed of a train is, the friction caused with the track lines. But here if you touch this particular maglev train, look at here, it is not touching the track. If this is the track, the train is little bit elevated. It will move like this on the track, not touching the track. Now interestingly, what is lifting the train like this? Diamagnetic properties of the track. Diamagnetic material means what? Something that will repel the external magnets. Let us see the whole summary here. I have taken a material, cooled it below the critical temperature, then it expelled all its internal magnetic field, then it became like a diamagnet. Because it is now a diamagnet, it will repel the external magnets. Because of the repulsion between the train and the track, the train will be lifted above the track. Without touching the track, it will move on the track. So with zero friction, it can achieve very high speeds. This is the principle in the magnetic levitation trains or maglev trains. This effect is, so what is the effect behind the maglev trains? Meissner effect. What is Meissner effect? The material expelling all its magnetic field when cooled below the critical temperature. Okay, right. Now we are discussing the properties of the superconducting material. We have seen one property, that is Meissner effect. Now let us see another property. This is not only a property, it will also explain how the superconductivity is achieved, how the superconductivity works. For conventional supercomputers or traditional supercomputers means low temperature superconductors, right? Okay, I might have used the word supercomputers once or twice because I regularly teach about superconductors in our comprehensive courses, and I hope it is quite clear and it won't be confusing, because clearly the topic we are discussing is superconductors, right? Thank you. Then, so the superconductivity works. Conventional superconductors, how the superconductivity works can be explained by a theory called as BCS theory. This BCS theory is named after Bardeen, Cooper and Schrieffer. Okay, these three scientists proposed this theory, therefore it is called BCS theory. This BCS theory primarily explains the Cooper pairs. Let us see what are these Cooper pairs. Clear till now? Then, when electrons moves through a superconductor, okay, let us suppose I have explained this Cooper pairs also. This animation explains about the Cooper pairs. What are Cooper pairs? They are the pairs of electrons. But actually, you know that electrons are negatively charged, and we know that like charges repel each other. Then how do electrons pair up? Okay, this is the question. In general, electrons are negatively charged. Like charges repel each other. So electrons are not supposed to form the pairs. But Cooper pair is nothing but pair of electrons. Cooper pair is nothing but the pair of electrons, isn't it? So, okay, this is one electron, this is another that is running, okay. These are the pairs of electrons, right. Now, how do they form the pairs? These electrons, when they move through a superconductor, imagine this is a superconductor. This box is a superconductor. Now the electrons are moving through the superconductors. Electrons moving through the superconductor. When the electrons move through the superconductor, they create slight distortion. They create slight distortion in the positive ion lattice. Okay, what do you mean by lattice? Lattice of a crystal. Lattice of a crystal means its three-dimensional structure. Three-dimensional structure or arrangement. Arrangement. It means when the electrons move through this superconducting material, they will create a little distortion, little gaps in the crystal lattice, the positive ion lattice of that superconducting material. This distortion creates a region of slight positive charge. It means if this is the superconducting material, when the electrons are moving like this, they will cause some distortion or gaps. Gaps in what? The positive ion, gaps in positive ion lattice, positive ion three-dimensional structure of this material, Now what happens? It will create a slight positive charge. It will create a slight positive charge. Here you will have slight positive charge, positive charge, positive charge, positive charge, positive charge, positive charge. This positive charge will push. See, for example, if this is that crystal lattice, okay, imagine this is a superconducting material, okay. In this, the electrons are moving. They created some distortion in the positive ion lattice. This distortion created a regional positive charge there. It means positive charge here, positive charge here. Now what will happen? This positive charge this positive charge will push the negatively charged electron like this, and this positive charge will push the negatively charged electrons like this. Do we actually have any attraction between two electrons? No. But the positively charged region, positively charged gap created in the positive ion lattice of this material will push the two electrons close to each other. So, though they do not have a direct attraction between the two, these two will together form a pair. This pair of electrons is called as Cooper pair. Cooper pair. Okay, so let us just go through this once. When an electron moves through the superconductor, it is moving through the superconductor, then it creates a slight distortion in the positive ion lattice, that is, it will create some distortion in the three-dimensional structure of that superconducting material. Then this distortion creates a region of positive charge. The positive charge will push the two electrons together, brings two electrons of opposite spin and momentum together, forming Cooper pair. These Cooper pairs can move through the material without being scattered. Okay, just like for example, you are walking on a road alone, you will get distracted by all the people around, all the things around. But if you are walking on the road with your girlfriend or boyfriend, then what happens? Without any distractions, without being scattered by anybody else, anything else, you will straight away walk through the road. Is it clear? Like that. Now that electrons are in the form of a pair, this pair of electrons can move through the superconducting material without being scattered by the lattice. This creates zero electrical resistance. It means the material can show resistance to single electrons, but the material cannot show resistance to this Cooper pairs. This is how formation of the Cooper pairs will lead to see how freely this pair of electrons are moving through the lattice. Okay, the lattice, it means the other structures are just making place for that moving Cooper pairs. That is how it will easily pass through the superconducting material. So what gives superconducting material the superconductivity? Formation of Cooper pairs. Which theory says this point? BCS theory. I hope it is clear. But this pairing is not due to the direct attraction between the electrons. Obviously, how can two negatively charged electrons be attracted to each other? As I told you, there is no attraction between these two electrons, but they are being forced to pair together by the positive charges present. Is it clear? Like this. These electrons are forced like this. These electrons are forced like this to pair up. Okay, forced like this to pair up. Okay, and interact via lattice vibrations. What are the lattice vibrations? You can see the blue color balls vibrating. Those are the lattice vibrations. Is it clear? So these electrons are pairing not because of the attractive force between these two electrons. They are pairing because of the lattice vibrations. How can you imagine lattice vibrations? Look at this animation. See the blue color balls vibrating. Those are the lattice vibrations. These lattice vibrations will force the electrons together to form the Cooper pairs. Then the Cooper pairs will easily pass through the superconducting material without having any resistance. These lattice vibrations are also called as phonons. Use the word once. This lattice vibrations, that is vibration of this blue color balls here, are called as phonons. Okay. Cooper pairs are single quantum mechanical system. Cooper pairs are single quantum mechanical system. Okay. First, let us try to understand what is a quantum particle. Quantum particle is the smallest unit of either the matter or the energy. It means smallest unit is electron, proton, neutron, subatomic particles, because atom is not the smallest unit of matter. We have smaller structures inside the atom also. So the quantum particles are electrons, protons, neutrons. Electron is a quantum particle. Smallest unit of energy is nothing but photon. They are the quantum particles. But now the Cooper pair, it's a pair of electrons. It's a pair of electrons. It means there are actually two quantum particles bound together, isn't it? It's actually two quantum particles, but they will behave like one quantum particle. They will behave like a single quantum mechanical system, meaning they behave like one single coherent entity. The Cooper pair behaves like one single coherent entity. Look at this animation. The two electrons are moving through the superconductor together as a single entity, as a single quantum mechanical system. The formation of Cooper pairs, requires extremely low temperatures. It means in any material, in this material, when the electrons form Cooper pairs, only when, look at here, in the superconducting material, Cooper pairs are formed only when cooled below critical temperature. Below critical temperature. Why? Because at the temperatures above the critical temperature, okay, at temperatures above the critical temperature, what happens is the thermal vibrations will break. The thermal vibrations. How to visualize it? For example, if you boil the water, you will see water molecules moving apart. As you increase the temperature, the movement of the atoms inside that material increases. These are called thermal vibrations. Above the critical temperature, the thermal vibrations will break the Cooper pairs. Cooper pairs. For example, electron, electron. If this is a Cooper pair, okay, then look at here. Thermal vibrations. Thermal vibrations will break the Cooper pairs. And if the Cooper pairs are broken, then the single electrons cannot travel with zero resistance. It means superconductivity is destroyed. It means if you heat the superconducting material above its critical temperature, its superconductivity will be destroyed. Why the superconductivity will be destroyed? Because the thermal vibrations will break the Cooper pairs. Okay, so let's just have a small recap of this. How the superconductivity works? Question: how the superconductivity works? Explained by BCS theory. Why this is called BCS theory? Because named after Bardeen, Cooper and Schrieffer, these three scientists. And this theory explains formation of Cooper pairs as a reason for superconductivity. Now, how the Cooper pairs are formed? You take step 1, take a material. Step 2, cool it below the critical temperature. At this below critical temperature, when the electrons are moving through this material, it will create a slight distortion in the crystal lattice of that material. In this distortion, a local positive charge will be created. This positive charge will force the two electrons to come together. This forms Cooper pairs. The Cooper pairs can travel through the superconducting material without being scattered by the lattice of that particular structure. This will give zero resistance because the Cooper pairs are not scattered, not distracted, not stopped. There is no resistance towards them. They will freely move without being obstructed by anything. This formation of Cooper pairs gives the superconductivity. But this Cooper pair formation is not because of the attraction between the two electrons. It is because the positive charge is pushing them together. And the Cooper pair will behave like a single quantum mechanical system. It will not behave like two separate quantum particles. It will behave like one single coherent unit and will move like a single coherent unit. The two electrons together will move like a single coherent unit. All this will happen when that material is cooled below the critical temperature. Now let us see reverse. If you heat it above critical temperature, the thermal vibrations will break the Cooper pairs. then what happens? The superconductivity is lost. Now the material is not a superconductor anymore. Okay. So how to destroy superconductivity? Okay. How to destroy superconductivity? One method is heat it above its critical temperature. Okay. There is another method, I will tell you later, but before that let us see this one. The critical magnetic field. Is it clear? So, the other method to destroy superconductivity is exposing it to a strong magnet. Exposing this to a strong magnetic field. Okay. Let us suppose this is a superconductor. It's a superconductor and it is kept inside a strong magnetic field. Okay. Once you keep it in a strong magnetic field, what happens is, okay, it will again create magnetic flux lines in that material. I hope you remember first Meissner effect that I explained. When you cool it below the critical temperature, what happens? All its internal magnetic field is expelled, right? The magnetic flux lines will disappear, right? But when you keep it in a strong magnetic field, they will reappear. It means what? Again it will change from its diamagnetic condition to a normal material condition. It's not diamagnet anymore. Okay, I repeat, listen carefully. What is Meissner effect? Take a material, cool it below the critical temperature, it will expel its internal magnetic field. Now reverse. If you heat it, that is one procedure, or if you keep it under a very strong magnetic field, again because of its influence, the magnetic flux lines will reappear. I mean, internal magnetic field will be again created in this. Internal magnetic field will be again created. Internal magnetic field created means what? Superconductivity destroyed. Superconductivity destroyed. Because the superconductivity is because it expelled all the magnetic flux lines. We have seen in the case of Maglev trains. So what is critical magnetic field? Earlier we have seen critical temperature. The temperature below which it will become a superconductor. Now this is critical magnetic field. What is critical magnetic field? It is the magnetic field strength at which superconductivity is destroyed. It means you have certain magnetic field. If you give stronger magnetic field than this, superconductivity gone. Okay. The maximum magnetic field at which superconductivity destroyed. Okay. So, the minimum temperature at which superconductivity comes is critical temperature, and the maximum magnetic field strength, above which the superconductivity is destroyed is called as critical magnetic field. But this critical magnetic field value is not constant. This critical magnetic field value depends on the temperature. At higher temperature, lesser magnetic field is enough to destroy the superconductivity. It means if the superconducting material is at a higher temperature, little magnetic field also, weak magnet also can destroy the superconductivity. At high temperature, weak magnet also can destroy the superconductivity. At a very low temperature, you need more magnetic field strength to destroy the superconductivity. It means at a very low temperature, you need very strong magnet to destroy the superconductivity. So critical magnetic field is the magnetic field strength above which, if you give stronger magnetic field than this, then the superconductivity will be gone. Okay, so that is critical magnetic field. Then another property of the superconductors is their high current carrying capacity. Superconductors can carry much higher electrical current compared to the conventional conductors. That means when compared to a normal conductor, superconductors can carry more electrical current. That is the reason why we can use them in MRI instruments, particle accelerators like Large Hadron Collider, etc. These are the properties of superconductors. Now let us see the types of superconductors. The first type is low temperature superconductors. These are the superconductors whose critical temperature is below 77 Kelvin. It means below minus 196 degrees Celsius. It means we cannot use the liquid nitrogen to cool this material below the critical temperature. We have to use another substance like liquid helium, which is much more cooler than the liquid nitrogen. We need a substance cooler than the liquid nitrogen to cool down this material below their critical temperature. Therefore, they are called low temperature superconductors. Second one, high temperature superconductors. Their critical temperature is above 77 Kelvin. It means above minus 196 degrees Celsius. Therefore, we can use liquid nitrogen to cool them below the critical temperature to get the superconductivity. The third type are called as room temperature superconductors. These superconductors are the material whose critical temperature is above the room temperature or above the 273 Kelvin. 273 Kelvin is nothing but 0 degrees Celsius. Those material whose critical temperature is above 0 degrees Celsius, like 30 degrees Celsius, something like that, then they are called as room temperature superconductors. They are more convenient for our applications. And in 2020, a material made from carbon, hydrogen and sulfur under extremely high pressure was identified as a room temperature superconductor. This is a recent discovery. Now that we have completed the types of superconductors, let us see the applications of superconductors. It means where all we can use superconductors. First one, we can use them in the magnetic resonance imaging. We use magnetic resonance imaging in medical purposes. That is, say for example, any cancer or a brain tumor, we have to take the image of that tumor. We use MRI. In the MRI machines, we know that we use strong magnets and strong superconductors are needed. Superconducting magnets, only superconducting magnets can be so strong. Superconducting magnets are essential for creating powerful and stable magnetic field needed for detailed medical imaging. Therefore, we use superconducting magnets in the MRI machines. We can also use superconductors in the SQUIDs, that is superconducting quantum interference devices. These SQUIDs are used in magnetoencephalography. Cephalon means brain, encephalography, that is to map the brain activity. This is also a medical application of the superconductors. Some superconducting devices called SQUIDs are used in magnetoencephalography, a medical technique to map the brain activity, how the brain is working. Then we can also use them in Maglev trains. In the beginning of this class, I have already explained how the Maglev trains work. Then we can also use them in particle accelerators. Superconducting magnets are used in facilities like Large Hadron Collider to steer and focus the particle beams. To collide two particles with very high speed, we need superconducting magnets. So superconducting magnets are also used in the particle accelerators. When two particles collide at very high speed, then only Higgs boson particles will be created, or the God's particles will be created only when the particles collide at a very high speed. Such high speeds can be achieved only in the presence of superconducting magnets. So we use superconducting magnets in the Large Hadron Collider as well. We can also use them in power transmission, that is electrical wires. If the electricity passes through the regular electrical wires, which are usually made up of copper, copper is a good conductor but not a superconductor. It means in the copper, the electrons will face less resistance but not zero resistance. There will be some resistance for electrons movement in the good conductors also. Because of this resistance, these electrons will experience friction. The friction will create heat. It means some energy will be lost in the form of heat. 100% electricity cannot reach the target destination. En route, some amount of energy will be lost in the form of heat. To avoid these losses, we not only need a good conductor, we also need superconductor. So we can use superconducting material in the power transmission. We can also use superconductors in the quantum computers. Superconductors are used to build the superconducting qubits. Superconducting qubits means quantum bits. Quantum bits. Superconducting quantum bits are fundamental in building the quantum computers. It means in building the quantum computers also we need the superconductors. And fusion reactors. What is a fusion reactor? In a fusion reactor, hydrogen will fuse with hydrogen to form helium. Two lighter nuclei will fuse to form a heavier nucleus. A heavier nucleus. I told you that it is two hydrogens will combine to form helium, but more precisely, the heavier isotopes of the hydrogen, that is deuterium plus tritium, will combine to form helium. It means two nuclei should fuse. We know that nuclei are positively charged, and we know that like charges repel. Like charges repel each other. It means two nuclei will not spontaneously fuse. We have to force them to fuse with each other. To achieve this force, superconductors are important. So we use superconductors in our tokamak reactors. Tokamak reactors like Joint European Torus Jet and also ITER project. In all these fusion reactors, we use superconductors. Next, superconducting magnetic energy storage. We can also use superconductor to store the energy. And superconducting shields. Superconductors can also be used to block the electromagnetic radiation. These are all the applications of superconductors. Now let us see the challenges in superconductor related research. First challenge is maintaining the cryogenic temperature. We need minus 196 degrees Celsius or minus 240 degrees Celsius. We need extremely low temperature. Most superconductors must be cooled, extremely low temperatures, often requiring expensive liquid helium, liquid nitrogen, etc. This is one challenge in conducting research in the field of superconductors. And another challenge is material fabrication and scalability. Manufacturing the superconducting material is difficult. Okay, if we manufacture superconductors, scaling them up, I mean producing them in large quantities is more difficult. Okay, and stability. I told you that a superconductivity will be completely destroyed when it is subjected to a greater magnetic field strength. So, superconducting properties can be sensitive to impurities, defects, magnetic fields, high temperature, etc. So, maintaining the superconductivity is also a challenge. With this, we completed what is superconductivity, examples of superconducting material, properties of superconducting material, types of superconductors, applications of superconductors, and the challenges in superconductivity research. That's all for this session. Thank you so much. Have a great day.